fun is to see how each of them affect the rate, but the biggest thing is you've got to make sure you keep the other thing constant. So if I want to find the effect of A, I need to look at two trials where B isn't changing. So I'm going to compare 1 to 3 because it stayed the same for B. A from 1 to 3 doubled. I chose to double it. And as a result, what did the rate do? Quadruple. So if I double a concentration and the rate quadruples, what does that order does that mean?
Second order. Did you get that? Did you get that, Taylor? Second order.
Okay, so A is second order. Now for B, same thing. Keep something the same.
Yeah, Newton would agree with you.
Okay, while the other changes. Now this time I doubled B, but what did the rate do? What does that mean order-wise?
0.
Yeah, 0 order.
Wait, I got that one right.
Oh, so you don't have
Look, I got that right. Oh.
I'm so dumb.
Oh my gosh. Oh my gosh. Oh my gosh, I'm so close. I didn't put rate equals.
Did you just put K, A?
Yeah.
You can get yourself a point still. That's okay.
Let's go.
Just don't do it again.
What
Okay.
if we...
Okay, questions on solving for rate law. Now, you are allowed once again to put B if you want, because it's 0 order, anything to the 0 power, right, goes to 1. So in a sense, yeah, you can dump as much B as you want in, and it's not going to make the reaction go faster, right? Questions?
I'm so happy I did that right.
Okay, now, just a reminder with AP questions and how they grade. If this was a free response question, okay, let's say hypothetically you're like, oh, I don't remember how to find a rate law. But you knew how to find K, but you can't find K without a rate law. Once again, this is where you won't be penalized for making the mistake more than once. So if you got A wrong right now, but you do the right process for B, you still get the point for B. Everyone understand that? Even though your number is going to be different from the number I get. Same thing for part C. Okay, for part B, we're trying to find the magnitude, which means the value for K. So you pick any trial you want, plug your numbers into the equation you just made. So I'm going to pick trial 1. 4.0 times
-3.
K is my variable, and then the concentration of A is 0.1. And don't forget to square it because it's the second order. Algebra to solve for K. 4.0 times 10 to the negative 3, I think it was. Does that sound right? Oh. Okay. Good? Okay. Sorry, I just didn't have the times to the negative 3.
Oh, that was
or,
Yeah, move the
point what? 004?
Yes, ma'am.
Also good.
I got it right. So I did it right.
Questions
The last one
on
was just
B?
stupid also.
So Taylor here's wondering why
No.
it's not -3. Because that's what he put down.
That's what I put down, that's true.
You like kind of had a part, I guess?
Whoa!
You don't
No!
get any points, but.
Good.
Okay, now let's talk about units here.
Okay, I figured it out now.
You think you got it? So, unit-wise, okay, coming back to this equation, I forgot to write in here, this is molarity is the unit on that number, okay? Now, the molarity gets squared and then divided over. So one of the molarities can cancel, so what you should have for a final unit is molarity, inverse seconds.
Actually, I got that right.
Or you can just use per
Because my
molarity
thing, I
times
actually got it
seconds.
right.
But the big thing is that the units are both on the bottom of the
She
fraction.
said units are half a point off.
Yeah.
Darn. I'm so close.
I can't say anything. I didn't even try.
Yeah, right.
So I didn't get those units because I had a different like exponent. So
So,
if I got the
because-
correct units for the exponent I had.
So
it's
yeah,
like-
you'd still get full points. Yep. That's where, once again, showing your work, you won't get penalized. We're making like one mistake over and over again. So, which honestly, I feel like how all things should grade, because it just makes sense. So, any questions on solving B or the units? Okay, and then part C is given these conditions, what would the new rate be? So we just found our K, so now we just take the same equation. Yep. 4 and then 0.05.
Don't act like you know things.
0.1, that's 0. That was squared. 1.0 times 10 negative 5? Yes. I'm recalling from memory from last period.
I never get that.
And rate is always molarity percent. I got one.
Really?
Questions on that? Okay, now here's how we're going to score it, because this is how I scored it last period, okay? We did it out of 3 just to estimate, but there's 5 bonus points available. Ready?
I'm still not gonna get.
So you get 1 bonus point for A,
Yeah.
Plus 1.
1 point for the answer, and 1 point for the unit.
Dang it, I only got plus 1.
Okay? 1 point for this answer, and 1 point for your name.
Whoa!
Oh, I have my name. Let's go.
Did you
I
forget
got
your
one.
name?
Yeah, I forgot my name.
No!
Oh man, I was trying to help you out.
I wrote my name right as you said it, so I think that counts.
If you know how to write your name, you can have your bonus.
Yes.
Okay, put your score out of 5 and slide it into the middle.
Oh.
How's that?
Wait, no, I'm gonna have a.
I got plus 2.
Got it? Okay, slide it to the middle and then pull out your note packet. Grab it for the
Even though I know.
Your sandal throw? Oh. Okay, pull out your note packet for me, everybody. Okay, before I forget, I'm going to have our new friends introduce themselves, because they're going to be hanging out with us for a while. And I didn't forget, because they've already done this twice. But, talk to you guys. So, okay, so close your mouths. Turn your eyes this way. Go ahead.
Hi, my name is Madeline. Please call me Madeline or Miss Tullis, and we're student teachers, so we'll be here through April. We're seniors at BYU. And I'm originally from Arkansas, and yeah, about everything.
My name's Abley Ellis. So we want to be science teachers, so we'll be qualified to teach biology and chemistry at the end of this. Hopefully, we'll be here till April when we graduate. I'm from Rexburg, Idaho. I don't live there now, obviously. We're in Provo, but
That would be kind of confusing.
yeah,
Long commute.
Yeah.
for real. And then I'm also pregnant, so I have a baby girl due in May, the end of May. So,
Okay, anything you guys want to know about him?
Neither of you do a backflip.
no.
Get on the trampoline.
Good question.
Because you said you grew up in Arkansas?
Yeah, so both my parents went to BYU. So, and I went to like EFI, BYU. Yeah. I just always wanted to move out for school. Yeah. Good question.
Any other questions people want to ask them? Once again, they'll be around a lot, so you'll get to know them.
What are you gonna name your baby?
That's a good question.
I know it's big.
We are kind of secret about that, so.
Oh, I have
It's okay, you
Not
can tell
sharing
me.
until we
Yeah, you knew Elon Musk, what is his name, is big X? It's like, yeah, that's what,
You know the AE that's combined?
Yeah.
It's so XAE.
No, I'm just kidding, look it up, yeah, he's the richest man in the world now.
Oh yeah, he just passed. Yeah. All the homies hate Jeff Bezos.
Yeah, how did he say it?
Like that.
No, I thought
Wasn't
they
it
called him like
Kyle?
Ash
Oh, they did.
Maybe Kai.
They call him Kai.
What? Just because they're like, let's give him a weird name and call him the most normal name.
Yeah. Dude.
It just spells with like the random letters on like special I feel bad for them. It's spelling
Yeah, honestly, what he said after, yeah, oh, yeah, back to work. It doesn't matter. It's just keeping
So
score
he,
at that
and
point.
his fault, if I were
No, I think it's
that,
chill.
I would feel sorry.
Really? He's like, oh, okay.
And he got like substitute teachers like this brought to me here.
Well,
I would die.
it's not about the money, you know?
He was watching like Celine Dion did like a concert on New Year's, and he was watching it and he got really drunk. And he woke up the next morning and he had legally changed his name to Celine Dion. Like he had gone online.
Okay,
like,
let's
he-
get back to
Not the circle! Not the
Can't remember.
That didn't. That's like somebody's
Yeah.
drama of the circle.
What a fun guy. I love him. He's a fun guy.
Okay, here we go, everybody. His girlfriend scares me.
Really? I don't know what his girlfriend is. I haven't seen her. Yeah.
So, as we continue this unit, everybody, really, we're going to be coming back to this concept of rate laws 2 other times, where there's multiple ways to get a rate law from a reaction. It always comes back to experimental data. I got you there.
Don't lie to me, Taylor.
No, I actually did. No, I printed out the notes, but I wanted the blue paper.
Oh, you're right. Have you heard that Jack Johnson song called Taylor?
No.
Oh, Taylor. Oh, it's about a girl. You must be so embarrassed.
Okay, so before we get though back into rate laws, we're going to kind of dive once again down to that molecular level of what's going on. So we mentioned last time this idea of a collision, right? That molecules have to collide to react. If they can't collide, they don't react. Or if something reacts, it means they collided. With this idea of collisions, though, what's interesting is we've only looked at what are known as overall reactions. An overall reaction, what we see in general chemistry, doesn't always show the full picture of what's happening with these collisions. So let's talk about, first off, 3 different types of collisions that can happen, or 3 different types of reactions. So when a reaction is defined by being a single process, okay, meaning one collision only, okay, it is known as an elementary step. Most reactions are not elementary. Most of them require, okay, this collides with this, then this collides with this, then this collides with this, then we get our product.
Nice.
Okay? But if it does happen in a single step, or those steps are broken down, they're known as an elementary process. Now there's 3 different types of elementary reactions. There's a unimolecular, meaning a single molecule is involved. Bimolecular for 2, meaning 2 things are involved. And then termolecular for 3 molecules are involved. Now the key word here, I know, it's not try, it's ter.
Why
Okay.
would you get more than that? Or
Then
do
it's-
you?
Good question, Taylor. I'll tell you what ter means, and then you tell me if you think it can really go past that. So a termolecular reaction, everyone, means that 3 things are simultaneously colliding at once in the perfect way.
Oh.
Yeah.
So it could happen, but it's not going to.
Yeah, termoleculars already are very, very rare. Because once again, the probability, visualize these bouncy balls flying through the air. Okay, that bouncy balls A, B, and C all hit each other at the exact same moment in the exact same spot they're supposed to hit. That would be very hard to happen. So anything past termolecular, and science I always say is possible, but maybe not probable. Okay? Yeah, is it?
Can you just make a catalyst to make it so you can make a 4-1 or something like that?
Good question.
One.
I'll double check this. I think though in adding a catalyst, it wouldn't be classified like, it still wouldn't provide the possibility of like, it's just the chance of like, can't find my words, okay, like 4 things all hitting the right way. If you think of 3, right?
Wait, we could demonstrate. What if like you gave
Yeah.
one to each person and we all tried to throw them at each other?
Or we could just run at each other, trying to check each other.
When I've always taught this, I've always imagined like those big like balls that you can like run into each other
Oh,
with.
yeah?
Right? Like we could be molecules and run
Never
into each
done
other.
it.
We should do that.
Yeah, you should.
Alright, after the AP test.
Wait, yeah, we should just take it out of the chemistry budget and buy like 4 of those things. Hamster balls. Just put them outside.
It'd be a good use of
I
money,
would do it
right?
Really? You looked out a wall and slided one of those?
So the other problem, Isaac, is you run out of places to bond, right? If you have 4 things all colliding at once, right, like you're just running out of space too. So not only like probability is hard, but like location, like where else would it bond on to? So good question though. So as we look at these, what's interesting,
Yeah, I could.
now do a big like highlight, circle, underline this word right here. Okay, these are being designated as elementary steps, meaning scientists determined it only takes 1 step for it to happen. When something only takes 1 step to happen, you can write the rate law for that step by just looking at the balanced equation. You don't actually need experimental data because the experimental data was behind finding that they're elementary. Okay, now this is where people sometimes get carried away and then they want to do this all the time. Okay, it won't work if it's not an elementary process. But when it does, it makes it quite simple because the equation pretty much just becomes the rate law where the coefficients become the order. Now, once again, these are some examples of the unimolecular, some bimolecular, and some termolecular, where termolecular can be 3 different things or 2 of the same and 1 of a different, but it still adds up to 3 different things colliding.
Wait, so if 2 of the same collided, like, wouldn't they just like be the same? Like, why would they change?
Yes, Taylor.
Like 2 of the same with another one that makes sense, but just 2 of the same alone.
I
Like,
think,
I feel like they would be happy in their molecular state.
so you're like, why would they?
Yeah.
Let me think
Why
of an
is this so
example.
funny?
If you think about like diamonds and graphite, the different
It's not funny, I don't know why
connections
it's
of
funny
bonds.
to
Let's see.
Oh yeah. Graphite and the diamonds bonds.
Yeah.
Yeah, I mean, it could kind of be like that. It's tricky though, because like, it doesn't really form from like colliding things, but they just.
Wait, would it be
exist that
like
way.
an oxygen?
Kind of, but then also oxygen doesn't exist by itself.
What?
Like,
You have,
Oxygen's alone.
There has to be a split second that it's alone, right?
in other reactions, yes. Give me a second.
No.
Oh, I think our next slide shows an example.
Oh, okay. That works.
I think.
sorry I laughed at you, it's just habit.
Oh.
No,
Poor
I didn't. I'll come
David.
up with one more check. Okay, here's what we're gonna do, ready? First step is looking at a reaction, you should be able to identify its molecularity. That means unimolecular, bimolecular, termolecular. And then write the corresponding rate law. So I'm gonna do the first 2 with you, and then I'm gonna have you try the second 2 for some smiley faces, okay? So first reaction here only has 1 reactant, so that would be classified as a unimolecular step. The corresponding rate law only shows the reactant, so it would be rate equals, don't forget little k, and then N2O4. Because it's designated as a unimolecular process, you can just write its rate law right out. Okay? This one has 2 NOs and and one O2. So this would be classified as a termolecular. Okay,
I know.
meaning rate would equal little k, NO to the second order, and O2.
Wait, so if it has the coefficient of a 2, you just put it 2? Oh. I thought it was gonna. Now I'm asking silly questions.
Okay, try the next two with your table buddy.
Alright.
Ready, set, go. Like amazing bond with itself, or like reaction with itself.
Yeah.
They have to be a team.
Why is the dry Because this one has 2, so there are 2. So that makes 3. It's like technically there's like no more. So this one would be
But they're all bonded.
Oh, here's an example.
Oh, I thought
You
that
find
this
it
one
in
was
this one,
one.
Yeah. Well,
Oh, this last one, yeah.
Well, you don't.
I had the card.
where does the O come from? Like an O.
So it'd be N.
So this is bonded all together. So N, O, and C are all bonded. And then when it collides with the cell, it breaks up into NO.
But where did this carbon go? Where did the chlorine go?
That's true.
Oh, I don't think that L's supposed to be there.
Uh-oh.
Oh my god.
Yeah, something's really wrong with that equation, Taylor. I didn't even notice.
Taylor,
I'm
you're
so good.
You're so good.
Stop.
We've been this whole time. There's been no Taylor.
Does that work?
There's been no brain.
Yeah, that.
There's been no brain.
And then the one above it, random oxygen appears.
It's just not right. Yeah, that one just isn't valid.
That one makes more sense.
Yeah, good observation. Last player didn't even point those errors out.
I vote I get 5 smiley faces for
I do, I agree. As long as I get 5%.
Oh, I forgot.
Not 5, but you can have 1.
Yes.
Oh, wait,
One
that's-
smiley?
Except there's no.
I can. Well, that means you don't get a shade.
1 per each.
Yeah. No. You can have
Okay, everybody ready to check?
Oh, sure.
Okay, if you said this was bimolecular, then that's my base. If you said this one was bimolecular, then that's my base.
Whatever.
Whoa, you just go around so many more blocks.
I don't have my smiley face.
Oh, I have yours instead.
Oh, no.
You see.
And this is
And then you can have a smiley face for each of your rate.
Can we just have a smiley face because, yeah.
Yeah.
What if we didn't put the L because it's not in the rest of the equation?
That's fine. Yeah. Okay, questions on rate laws from elementary six?
Not that, well, I've used that.
So 4 smiley faces a day.
I've already used
Oh,
it.
yeah.
1, 2.
Oh, no. Not the brother, please. You got the.
I realized it before.
Okay.
Yeah. So you have like 35. You could just not try.
Okay, let's look a little bit more at these different types of collision reactions and what's going on. Okay? So, we talked about last time that the reactions or the molecules have to be oriented the perfect way in order for the reaction to occur. This is why, once again, the majority of collisions that happen, nothing happens. Right? When you break down like the probability of something reacting, it's like, seems quite low. Because they have to collide in just the right way so that the bonds that they and the bonds that need to break can break. For example, in this reaction, the chlorine is going to bond with that chlorine. So if this chlorine molecule hits anywhere else, it just bounces right off.
Wait, so is that chlorine, like, doesn't chlorine have to be attached to something too, generally?
Yeah, so this is where it's like showing just an intermediate
that's what I
process.
thought.
Yeah. No, good question though. Yeah, Zach?
Dang, Taylor.
Does does stuff ever like get 100% bonded, like change?
Oh, like, you can, like 100% yield pretty much. Yeah, it just has to be often like in a very controlled setting, and stuff like that. So, good question though, yeah. But this kind of shows you why sometimes it can be extremely hard to get high yields of these. And depending on the type of reaction, that can really affect like how hard it would be. So if you think back to like our silver lab we did last unit, we had a pretty high yield with that one. I think it was like 90 something, right? But in that lab, all it was you had the copper wire, so this was one, right? And then the little crystal screw on it.
That was so cool.
I love that.
Okay, so all it was is the copper just needed to react with the silver that was floating around. So this is why this probably has a much higher chance of yield, because it can hit in a lot of ways and still bond, right? So, good question. Now, the second factor, besides the orientation of our molecules, is the energy. So there's a minimum energy that needs to be paid in order for a reaction to happen, and it is known as its activation energy. Without that minimum energy, the reaction will not start. You can think of it as its ignition. It's the kickstart to make it happen. Upon these collisions, this is what used to help break chemical bonds. Now, something that's fundamental that we need to make sure to understand as we're talking about energy again is the idea of breaking versus forming bonds. Okay, I left it up here from last class, but to break a bond takes energy. You have to put energy into a molecule to get the bonds to break. When new bonds form, energy actually is released. Gavin, you had your hand up.
Yeah, I was just gonna ask how you say the guy's name.
Savante Arrhenius?
Cool.
Is
And
that how I
now
would
just
say it?
quick trivia, do you think he has a mustache?
Yes.
He does, correct. Look at that guy. What a face.
I guess this is like stereotypical. I'm pretty sure he's Russian.
He's Swedish. It says right there.
Oh, it says it there? Lots of them are Russian, so. And I had no idea he had a mustache.
Yeah, he ties his bow tie so weird. Is that just me?
I don't know.
Look at that bow tie.
Okay.
Oh, wow.
Now, with this concept, Kate, once again, make sure that you change your logic if you have, sometimes I feel like we build this bad conceived idea through science of that a molecule is like a popper, like a firecracker. And if you pop it open, energy comes out. Okay? That's backwards to what's actually happening. You have to put energy into it. When those molecules then bond with new things, if it's a more stable arrangement, energy can come out. But it's a balancing act between breaking and forming
Bless you.
to determine that overall energy. Now, before we keep talking about energy, let's talk about, we looked at these graphs before in Unit 3, I think it was, of the speed distribution of molecules. And how we talked about here, so here's kind of your example. So here's what the different colors show. Okay? That lighter molecules we've talked about have a much greater distribution of speed. Versus heavy molecules, right, have a very small distribution. Okay? Or vice versa, coming to this graph here, higher temperatures have a greater distribution of speed than lower temperatures. So in this graph right here, T1 would be less than T2 in terms of value. Or in a sense, T2 would be hotter than T1. The hotter you make a reaction, the greater distribution you have of molecule speeds. Okay? Now, for a smiley face, don't say it out loud.
Yeah, Taylor.
Okay, think in your head.
I feel like teaching.
going to the molecular level, why does increasing temperature increase the rate of a reaction? Once again, molecular view wise, okay? Think in your head for a second.
Oh, dang it.
It's not the most.
Why does increasing temperature increase the rate of a reaction at the molecular level? Okay, turn to your table buddy first and tell them what you're thinking. Go.
Yeah. It's more probable that if they're all
More times they have to get the reaction.
Wait, you mix salt and water and start to
Yeah.
No. Yeah, what is it? That's not salt. Oh, you're boiling salt and water.
Okay, Gavin, do you want to share?
Yeah.
Okay, everyone listen to this, and if your answer, well, I guess we'll see if it's right.
Yeah, if I'm correct.
Your answer is like Gavin, then Gavin just throw that somewhere.
Okay, why at the molecular level, Gavin, does temperature make them go faster?
Because the higher the temperature, the faster they're moving, so the more chances they have to hit correctly and do the reaction.
Perfect, great answer, right? The faster they're moving, the increase that probability of them hitting like they need to. Good, have a smiley face for that. If your answer is like that, you can also have a smiley face as well. Anyone have a different answer? There's two ways you can answer this question.
He talked about them hitting the right spot.
It's kind of a similar idea of increasing that chance, but right idea still.
What about like, actually, no.
Say it, Taylor.
Come on, Taylor.
Taylor,
I
you
was thinking
chicken.
well, I was just thinking higher energy means that like maybe the electron could jump to the next level, but I don't know how that has anything to do with it.
Whoa, that gets a little deeper than I want to go.
Dang it, Taylor. I thought she was just gonna say you're flat out wrong.
But then
I got
I-
excited.
Taylor, you're too smart.
I'm too smart.
Okay, we're just gonna sidestep that for now. We can answer that later. That gets into like, whoa, but you are right, kinda.
Dang it,
Let's
Taylor.
That's actually a
go!
really good thought.
No, you don't get another smiley face.
So the other factor with collisions we need to be aware of is so two things can collide, okay, in the right way, but still not bond if they don't have enough energy to break and form new bonds. So that's the other thing temperature does is it provides them with enough energy to make that collision successful. Okay? So what we're gonna do is we're gonna learn how to interpret what are known as these reaction energy profile or pathway graphs. Okay, so turn to this and let's do some labeling here.
Whoa, this blank was filled for us.
I filled one in.
Yeah.
Oh, look how nice.
You're the best. Christmas came. Is this late? When does it go from late to early? Just the very center? The center? Okay. The middle, the center of the year? What am I saying?
Okay, so we're gonna look at a variety of these graphs. But the key patterns are the same of what they represent. The starting line, oh, not reaction, what the?
Oh, dang it.
Oh, that's what I put. A reactance.
There we go. Okay, so the starting line represents the energy of the reactant, so how much energy those molecules have. The ending line represents the energy of the products, okay? The line is showing you how the energy changes as the reaction is proceeding. So for this particular reaction, I'm putting energy in, hence the climb. Then energy is coming out. Okay? So overall, the overall energy changed is measured right here, and symbolically it's known as delta H. We'll talk a lot more about H. You could think of it as representing heat. It doesn't actually stand for the word heat, but it helps because it's letter H.
That's true.
But it's the overall energy change. To calculate the overall energy change, you always do the energy of the products minus the energy of the reactants. Now what that means, particularly in this example, because my products are lower than my reactants, you could end up mathematically with a negative energy value.
Can products ever be higher than reactants?
Yes, or it could be the other way. be products are higher than the reactants. What does it mean scientifically to have a negative energy change?
You lost energy.
Good. Used, lost, released, it's the direction thing again. Right? Kind of like what we talked about with rates, right? You can't have a negative rate, but the direction can change. Okay? This right here, this measurement from the start to the hill, which means that's how much energy I had to put in to get it to go. This right here is the activation energy, which we symbolize by E little a.
Sports. Get in the game. It's in the game?
It's in the game.
Oh, that's right. You're right.
Okay?
That should be AE.
Yeah, AE test.
So the activation energy is determined by subtracting the peak from the reactants. That's how you can calculate what the activation energy is. Now in terms of, like, once again, molecular view-wise, the downhill in chemistry is pretty much instantaneous. Okay, once you give the molecules enough energy to get over the hill,
It's just a 90 degree.
they just,
It's just like a cliff.
90 degrees.
kinda. I mean, in terms of our view, right? For
That's
molecules, it's like maybe gradual, but
good for
pretty
them.
much it just goes forward, okay?
Slow down.
That's why once again, that is the minimum energy. Maybe we'll write minimum here.
They were. Yeah, in JoJo, Dio sand actually slows it, like, and stops time.
That's pretty cool.
And no, it's a big deal.
So with this
You
idea,
just have to watch it to know, okay?
just
Don't
gotta
judge me.
watch JoJo, I guess.
Yeah! It's super
I
good.
don't know. I don't know.
JoJo's Bizarre Adventure. Okay.
Still don't know.
It's an anime, okay?
Oh.
Yep. The disappointing side. Anime.
Sorry, Gavin. Okay, now at the top of this hill, an interesting molecule is created, right? This in that box up there. Okay, we have what is known as the transition state or the activated complex. Same thing, just two names. Activated complex. Okay, what that is it's kind of the in-between where some bonds start to break and some bonds start to form, so you often get like these in-between molecules where they're not the reactant, they're not the product, but they're in that transition phase. But the transition state is not stable, hence why it's the top of the hill. It is very hard to isolate a transition state molecule.
Like made it absolute zero the second one was like that.
Yeah, so you'd have to like somehow control the reaction in such a way that you like stop it, but
Absolute zero, no big
hard to
deal.
do.
Excuse me, what?
Okay, anything else? Did I miss any other labels? Wait, you meant to put that on the top one?
Oh, I'm good, thank you.
Yeah, put this in that. Oh, sorry. Tony, one of these days I'm gonna make the whole thing a whiteboard. Yeah. And then get a ladder. And then I can write everywhere.
I don't see any harm in just writing on the brick.
Just write. I thought it'd be cool if you get one of those like ladders like on
Yeah, no,
each
you should
that,
get like those, you should
Yeah.
have just a
Yeah.
whiteboard that like goes up and down.
Yeah,
Like you have two whiteboards and you just pull the second whiteboard down, so you don't need to have a ladder. You can just push it up afterwards, and it's like you have two whiteboards, but you
But
don't
my
need a ladder.
screen's up there.
Yeah.
So I have to go-
Move
There you
the
go.
screen, you use it.
My projection is up
This is a
there. That's
little
what I
too
meant.
complicated.
Because I want to write in that box.
Oh, I guess you just make the,
Yeah.
you just move the entire whiteboard up like a foot. 'Cause the bottom of the
Wait, what are you
whiteboard-
saying?
That is
Or-
true. That is
or
true.
what
As you
about-
say, because this never gets shown.
How about we just move
Or-
the projector down?
Or
That
you
would be
know,
the easiest way. Well,
Yeah.
mine is how it looks.
It's like, you guys are all.
but the first option was.
The letter would be cool.
Yeah.
So, okay, let's try this practice problem for some more smiley faces.
what was at the top?
That's what we were talking about. So this should be in that
Oh,
box.
Oh, that's so obvious.
I know. That's what we'll do.
Activated complex.
Okay, with your table, buddy, answer these two questions with these three graphs. First step, label each one as releasing or absorbing. And then question 2 says rank the graphs in order of fastest to slowest.
Alright, I got this.
Okay, you can talk to your table buddy if you so desire.
So I think these two would be really easy.
And then the next one, the
Okay, but that's, so I guess maybe which one is this?
Our anime is not that weird. Okay?
So,
I don't really know what's that. Maybe. Yeah, because this one says
Set your pens down when you're done.
All your birthdays, all my roommates.
so it would be more
I guess this one has the highest speed, and this one
Yeah,
doesn't.
but that's the.
But I don't know.
Yes.
Taylor, how do you know which one's faster?
Okay. This one's smart.
I don't know. Let's just measure.
Yeah, because this has a lot more parameters.
2, 3.
Yeah, but like this is also affects it. They also it just like so it could be there and this one.
Okay, good enough.
Isn't that scary how we just automatically do that? You know, just,
Scary.
it's like we're brainwashed.
I know, I find it very helpful.
I think it's scary. Like, if you do it to a person sleeping and they just like,
You think that rhythm is universally accepted?
yeah,
Like-
knocking on doors.
But like that rhythm, like, could I go to Mexico?
Well,
Let's do
Mexico's
that.
too close to the United States. It's like,
Yeah, you gotta go to
Go to
Japan.
Iraq.
I go to Iraq.
Yo, dude.
far enough away from the United States.
Dude,
That's a
my,
random question, but like it's such a weird, universally accepted rhythm, right?
Maybe, I don't know, I haven't traveled outside the US, I don't know.
yo, dude, my uncle. he
Anyone have friends
went
outside
on
of the US?
tour there or something
Something?
in Iraq.
Curious.
I don't know. Guess he was a fan or something. He went on tour there.
Okay, doesn't help.
He didn't like it very much.
Okay, here we go, everybody.
It's not fun.
Give me your attention back this way.
Oh my gosh.
Okay, let's check our answers. I think we're pretty good on the absorption and releasing section, but let's check it. So this one you should have said is releasing. This one is releasing, and this one is absorbing or negative.
I think 3 smiley faces.
Okay, one smiley face each. Okay. Questions on that? Okay, now I'm gonna pick on Winston because he had a good light bulb moment. No, it's a good theme.
He's a beautiful boy.
Okay, so why? Explain how you determine slowest to fastest from the graphs.
Well, I was looking at the graphs, and you said that it releases really fast, so once it's on the downhill, it'll just go fast. So I was just looking at which one had like the tallest left side, because that's when it's gaining enough energy. And so the middle one would be the slowest. The one on the right is the middle one. It's like the second slowest. And then the one on the left is the fastest.
Yes.
Perfect. So what he's saying for those that couldn't hear all the way,
Oh, that's
okay, is the downhill really doesn't matter when it comes to the speed. It's all about the uphill, and if I put the same amount of energy into each, the one with the lowest activation energy, so here's your connection, okay, the lower the activation energy, the faster the reaction will be. Because that's what needs it, that's what it needs to get going. And so once it has it, then it just continues onward. Questions so far?
Like BT.
So you can have 6. We'll do, so you get one of each for one, but then I think just one smiley face for the right order.
Never mind.
It's kind of like you got it or you don't on that one. Okay, last piece to our puzzle here, everybody,
Is that what you want me to do?
Wait,
is
so how many stars?
combining steps into an overall. Okay? Now, just so you know, you will, in this class, you are not expected to come up with steps of what's known as a mechanism. A mechanism shows you, hey, this is going to hit this, then this will hit that, then this will hit that, and then you get your overall. What
So
we
it's
need to
like
be able to do,
The other side of elementary.
yes, it's like combining all the elementary into the big picture. Okay? What we need to be able to do, though, is combine and identify what the different pieces represent. Okay? So, first thing to combine in an overall reaction, we're going to literally add these two together. But what we want to pay attention to are two different types of themes. If you have two different colors right now, it might be helpful to circle them like I am. If not, maybe then draw two different shapes.
Squares and circles.
There you go. Okay, so I'm noticing this, ready? NO3, that marker's not the greatest, is produced in step 1. I create it. But in step 2, it then gets used up. So I made it, and then the reaction used it, which means it's not part of the overall look. Okay? On the other hand, I also see, let's get red here, that NO2, I start with 2 of them, but then I did boxes again, I meant to do circles, but
Oh, dang.
NO2 is there in the end, okay? NO3 is what we call an intermediate in the reaction. It's not a reactant, it's not a product, but it's made and then used, an intermediate.
Is NO2 an intermediate too?
It's not.
It's a
It's an extermediate.
Any idea of what NO2 could be classified as?
extermediate.
Something I put in, it's kind of like spectators.
Oh, a viewer.
Any thoughts?
Home, yeah.
So something I put into a reaction, think about last time for those that were here. There it is, Kimberly.
Oh,
No, I think we should go with stop.
So catalysts are something we put into a reaction, but they still
Oh, I
come out of the
wrote
reaction. Okay? Which means they're not included in the overall either. So I'm gonna have NO2 for this one, plus CO, NO, CO2.
I can't. Catalyst. Oh my god.
Okay? So catalysts we start and end with, they help the reaction happen, but we don't write them in the overall. Now this one's an interesting catalyst because the catalyst is itself,
Yeah, there's NO2.
right? By adding more of this, it helps the reaction
Oh, yeah, that makes
happen.
sense.
Yeah.
Science.
But in the end, you'll get some of the stuff you put in back out again.
Wait, wouldn't the catalyst be required for the reaction though?
Some reactions, yes. In this case, with this mechanism,
Like if you only have one NO2 in the whole thing, you would need the
Yeah.
other NO2.
well, it could, because in a sense, you're never gonna like, I'm not pouring in like a single molecule, right? So let's put a number here, like if I have 10 grams of this, right,
Okay.
it would happen. But if
like,
you don't have a minimum amount, yeah, it would be limited for sure. Yeah.
Is there supposed to be a subscript on the NO2, on the NO in the product?
No.
On the bottom?
No. Okay, so this one we keep out because it's a catalyst, so it's just.
Okay.
Does that make sense?
No.
So it's kind of like the idea of spectators where we're canceling out the things that appear the same on both sides,
Okay.
but keeping what's different. So I'm canceling these out, I'm canceling those out, and then I just wrote
Okay.
what was left. Does that help?
Yeah.
Now what's interesting is when we start getting into multi-step processes, we're gonna start getting graphs that now look.
Oh,
Oh,
no.
that's a little fun.
No.
It's like a roller coaster.
Yeah, it's like the McDonald's sign, but like,
You know what
it's sad.
What if it was like
It only matches. So what this represents, everyone, is this first peak corresponds to the process of step 1.
Oh.
The second peak corresponds to the process of step 2.
This is
So
bull.
when you have 2 steps, you have 2 activation energies.
Is it just me or is saying bully is like difficult? Like bully.
It's like hydroplastic.
Yeah, hydroplastic.
So we have EA1
Yes.
for the first activation energy, and EA2 for the second activation energy. This valley is where that intermediate gets made. And notice, because it's a valley, they are something that can be stabilized.
I thought they were called troughs.
That would actually be a good, better. I
Trough
think
is
that would be
also
kind of cool. Like a trough.
Yeah,
We should change its name to trough. We should
It is
petition.
called a
do you know what a trough is?
No.
It's what pigs eat out of.
Yeah, I know, but they still call it a trough.
Wait, I thought you just said you didn't know what a
No,
trough
I thought you
was.
meant like a trough.
Okay, last practice
Oh my
quiz.
god.
Before we go, ready? Try exercise 5.7 for the bell rings. Ready, set, go.
What's on the second lap?
You got 1 minute. You got it.
C plus F. C and F. Oh, yeah, I don't know.
Did I do this right? We can cancel out. So
Oh, wait, then we have to, which one's the catalyst? The top one.
do we have to label what they are? The ones I
Label of catalyst and intermediate. So if there are those, identify them.
Let's go, I beat Taylor.
Catalyst.
It only matters if we got it right.
You just take out the ones that
Wait, you have to do both 5.7s?
Boom, down. Oh yeah, there's 2 5.7s.
Oh, there's 2.
Well, one is
We
the
have to do
example. And one is the.
Oh no, it's okay.
Okay, we'll check these and do these right at the second one on the start. Okay, but this is what these quizzes have a lot of reactions like that where you're combining, identifying intermediate.
I think I'm. Oh,
So I
Yeah? Good for you. Yeah,
that was good stuff last class.
I know, I remember really well.
Okay, everyone say goodbye.
Bye.